Okay, so good morning, everybody. Welcome to the second lecture of natural language processing with deep learning. Happy to see so many people here on the second week, which is not the rule most of the time. Anyway, so as I told you yesterday, we're gonna dive a little bit deeper into the background of mathematics, because we do need a good understanding of the mechanics behind deep learning and training deep neural networks, which is something which is important for if you want to do NLP with deep learning. So today we're gonna deep dive a little bit, but as we talked last week, you're not scared of a little bit of mathematics, which is great. So let's jump into that. So motivation. Okay, first, let me just ask if any one of you knows stochastic gradient descent. Anyone heard of this before? One, two, okay, great. Is there people who never heard of stochastic gradient descent? Okay, this is great as well, perfect. Okay, we're gonna cover that. So if you ever heard of, so the two of you, if you ever heard of stochastic gradient descent, did you ever try to implement it? No? Okay, why not? Why not?
Didn't need to.
Didn't need to, yeah, okay. How about you? Same. Yeah, the point is like we don't want to implement it unless you really want to maybe understand it or play around with that algorithm and stuff like that. Mostly these are implemented in libraries which you're using, such as, I don't know, Torch, TensorFlow, or any other kind of machine learning library that you're using for deep learning. So you don't want to reinvent the wheel. But there's a difference between reinventing the wheel and trying it on your own in order to understand it. So, you know, I'm not saying you should do that, but I can guarantee you after this lecture, you should be able to implement stochastic gradient descent from scratch by your own, maybe, you know, with a little bit of effort. Okay. And the question you might be asking, like, what, you know, so we were talking last time about what was it, like tasks, right? Then what was the other part? Metrics, right? So we talked about evaluation of NLP and the different tasks and what NLP is trying to solve. And now we might be asking, like, why the heck are we talking about stochastic gradient descent? What is that? So how does it relate to previous lecture at all? So it doesn't relate to the previous lecture at all, but it's a feature, it's not a bug. Because we are setting kind of the scene of things that we might be doing in the overall course, which task we want to solve, but now we are going into the very core of the mechanics of these deep neural networks and how they work. So we need to understand them to build upon. And I guess in 2 or 3 lectures, we will be able to connect the technical knowledge we have with the task we want to solve. So we'll be talking about that as well. Okay, so there's no direct connection to the previous lecture, but we're coming from 2 different angles to end up with the same goal. Okay. All right. So how deep we will go? Well, okay, so we won't cover many things from mathematics. I mean, you had some calculus, algebra, and stuff like that already. So we won't cover set theory because we know there are some sets and elements and tuples and stuff like that. So you should know that. If you don't know the set theory, just look it up. I mean, it's we don't need that much, so we won't cover that. We don't cover numbers, so we kind of assume we have numbers, we have real numbers, and we have this ugly infinity, right? So it exists. We don't want to explain that. And also, there are some sequences of numbers, and the sequences of numbers have limits, and functions also have limits. So this is something you should have already covered previously, but we will deal with that a little bit today. Also, a little bit of notation. So what is this thing? It's basically saying it's a tuple of, let's say, real numbers. So for example, this is a tuple of real number, right? So we're using this parenthesis notation with a comma in between. Why not? It is also like a two-dimensional vector, so there should be no surprise. Is it any surprise on this slide for anyone? This is good. We have a common ground. This is important. All right. So the problem number 1 we're going to tackle today, well, the biggest problem we want to tackle today is how to minimize functions. And now, why? Why do we care about minimizing functions? I mean, functions are something mathematical, and we want to build models that, like, we want to build GPT. So why do we care about minimizing some functions? Like, what the heck is that? So we are in the area mostly of supervised machine learning, which means Anyone who knows why we want to minimize functions, by the way? I mean, we talked about stochastic gradient descent, so maybe those of the two of you who had this before know something about why is it important. Maybe you don't. So because we typically have some training data. And the training data, I mean, we talked about it last time. So we have a data set, and there's a training and def and test. So we have some training data, and we want to learn on this training data, right? So for example, for classification. Then we have some sort of learning algorithm, whatever it is. I don't know, it could be something that learns from the data. And the point is that we want to, if we training on the data, we are getting maybe some errors, such as misclassifications, where the model or the algorithm is trying to learn something from the data and makes mistakes. So it's seeing the data and saying, well, maybe I'm gonna on this picture, or there's a cat, while it was a dog, or oh, this document has this review as positive while it's negative. So there is some errors, some misclassifications, and obviously we want to minimize these errors. We want the algorithm to learn as best from the training data as possible. So we want the algorithm to really mimic what's in the training data. If it reads a document with a negative review, we want it to say, oh, it's negative. If it reads a document with positive review, oh, it's positive, okay? So there's some error to be made, and we want to get rid of this error, which means we're minimizing the error. Okay, you're with me? That's why we care about minimization, because we want to minimize some sort of error during training. Oh, okay, cool. So we want to minimize stuff, and we now need some sort of formalism for this minimization. And we are kind of projecting our learning problem as a function. Okay, so we are having function, and we want to minimize the function. The function is this error function, whatever it is. We'll talk about it later, but we want to minimize some function because we want the error as low as possible. Are you with me? Okay. This is great. So we just need to minimize the function. It's something we know from calculus already, or maybe not, whatever. So the problem is, let's say we have any function. Now we have this is a function from reals to reals, and this looks like that, and maybe it looks differently somewhere else, but it has a thing which we want to find. So how is this called? How is this thing called? What is this? I know it's Friday morning. Yes, you. It's a minimum. It might be local, right? I mean, we don't know how the function looks like, but maybe it's a global even, but maybe it's a local minimum. Okay, cool. And so if you're minimizing a functions, we want to find the minimum. So what a minimum actually, what does it mean? It just means that the value here of the x gives us the lowest value of the f. So if we have y is fx, then at this point we get a minimum value of y. I mean, that's kind of easy. So if we have easy functions, whatever they are, so for example, if we have, I don't know, easy function, oh no, like that. So it's x squared. It's super easy to find a minimum. So I think you had it in already in calculus or somewhere else. So easy functions are easy to, you know the techniques already. There is a so-called clause for a solution. So you use derivatives and stuff like that. But for complicated functions, it might be not trivial. I mean, it might be cumbersome. So we want to do that, okay? So we want to find a minimum of any function. All good so far? Nice. So as I said, we have so what is a function now? What is a function of a single variable, right? And just make it very clear. So we use typically the Euler's notation, which is somehow standard naming. So we have some standard naming conventions, like x is the input, y is the output, and f is the name of the function. Okay, arbitrary. Somebody just made it up 300 years ago, and we're just using that, right? So okay, so which means we are using this sort of y is equals to f of x, and this notation is saying, well, okay, there's the function is from a domain to a codomain, where it goes from reals to reals, for example. Okay, so this should be pretty clear, but just about the notation, like, because the notation is somehow a little bit chaotic, in the whole field of function minimization. And we have one thing which is called a, we can compose functions together. For example, we have two functions, one f from reals to reals, another is g from reals to reals. Then we might use this sort of symbol called, how's it called? It's a circle, I guess. I don't know if it has a name actually. It's a circle, at least in LaTeX. And what this means is that function h is a composition of function g and f, and it basically means that you first evaluate your input on function f, and then plug it into the function of g. Okay? An example of that. Can you think of an example of what this could be? Yeah.
So function and its inversion, kind of linear map, and then we invert it, and then we want to compose them and say they're the identity.
Okay, something more simpler, something super simple, like super simple.
X squared plus 2.
Okay, yeah. Interesting. X squared plus 2. So this would be what? So, in this notation?
Yeah, so we got x, then we square. So that's the first operation, the f.
This is f.
So squaring x.
Okay, and then this plus thing is the g, something like that. Maybe. Yeah. Okay, so we have multiple operations. This is easy, right? Just the notation, if you see something like that, oh, okay, yeah, it's getting complicated. No, it's just function composition, but you have to, get used to it, like the circle operator, okay? All right, so we can combine function. This is great. That's what we're gonna do. Now we have to talk a little bit of lines as well, because we can use some sort of geometric interpretation of many things here. And so it is that lines in a Cartesian plane. So we have Cartesian plane, x, y, and there's points. So lines here, what is a line? They're characterized by a linear equation, by linear equations. So the definition is that a line is a set of all points. So this is a set of all points such that they satisfy this linear equation, right? So they're saying, well, some coefficient times x plus some coefficient times y equals to some other coefficient. This is a linear equation, and all these points that kind of satisfy this linear equation, given these fixed real numbers, the coefficients are on this line, are this line, these points. Okay, so this is a standard kind of definition of a line in 2 dimensions. Okay, any questions? Good. So we know what a line is. What's next? Yeah, okay, this is interesting. So we don't typically, we might be using this standard notation, this sort of definition of lines as a set, and typically we use this so-called slope-intercept form, where we turn this equation into, we just move the W3 on the left-hand side and then move the x on the other side. So we have something we know as a function y equals to something. Okay. Well, and this is a linear function because it's a line, right? This is why it's a linear function. It's a line. Does it make sense? Because we can just, do a little bit of arithmetic and end up with a line. So, okay, so y equals ax plus b, and we just change the names from w1, w2, and so on. Just use the a and b, which are called, this is the slope, and this is the so-called intercept. Okay, and I'm pretty sure you've seen that many times before. It's a line in 2 dimensions. Okay, cool, a function, linear function. And the linear function has something which is the slope, and it's interesting to see, what a slope is actually. So what is the kind of angle of this function, if you will? And if you look into trigonometry, I guess, or high school mathematics, we have a triangle here, so 90 degrees here, and we might compute what is the a in terms of the angle here, and I have the answer already here. So, but you would end up with that definitely. So it's run over, how is it in English? Run over rise is the tangent of the angle, something like that, right? This over. Sorry, this over this is tangents of this theta, right? This is trigonometry. Okay, cool. So now we know that a equals to tangents of this angle. So we know that in this equation, the slope actually, which is a real number, corresponds to actual angle. So we have an interpretation of this slope. So what does it mean? Well, the a could be any real number, but obviously this could be everything between 0 and 180 degrees, right? You know, or 360. I don't know. Well, tangents has some sort of range, right? Okay, so we know what the slope of this function is. Any questions? Is everybody with me? I know it's very early in the morning. I'm sorry about it, but you know, I think we'll manage. Okay, so we have linear function dimensions and we have a slope of that. Why is it important? That's a good question. So the goal is now, the sub goal is that we want to approximate a function by a line at a point. Okay, we can do that. So let's pick a point, for example, here. And we want to approximate this here by a line. Okay, so this would be like that. So basically a tangent here. And this will be a steepness of this function at this point. I mean, this function is not a linear function, it's some sort of nested function, but we want to have a steepness at certain point. So how can we do that? And we're going to use the derivative of the function. So the derivative of the function is a limit where, okay, let's say I pick 2 points here. One is going to be x and one is going to be c. And of course, I can sort of make a small triangle here, and the slope, as we saw here, so the slope will be the rise over the run, right? So this is how we get a slope. We can do the same thing here. So we take the differences between those two things over the difference between those two, x and c, okay? And make a fraction. So this is going to be exactly here. We're subtracting f of x, which is here, from f of c. So we get the height of this triangle divided by the length here, by x minus c. Okay, that's easy. The point here is that we're getting this difference very, very small. So we're kind of taking the limit and making this as small as possible using the limit. That's why we end up with a slope at this point c. Okay. Is it clear? Any questions? I mean, this is something you might have covered previously in calculus, but just repeating how we end up here. And we get, you know, using this derivative of the function f, which we use this symbol. How's it called? This tick? F what? Prime. It's f prime. So f prime is a symbol. Sorry. I think the mathematician would say prime for the symbol, but not for the derivative. Yeah, it's a prime. It's a symbol. It's a prime, f prime, but maybe not for derivatives. Okay, whatever. But we use this prime symbol for derivatives as well here. We have different notations, which I'll show in the next slide. But anyway, so this is the derivative of function f at point c, which means whatever, if I use this function for computing derivatives, whichever point I'll take, for example here, and compute a derivative f at this point c, I'll get a line. And here this line will be something like maybe a constant line or whatever. So I can use this derivative for give me any steepness at any point. Okay, you're with me? Sounds great. So obviously we can use this limit to compute this, you know, the limit for computing c at every point for any function. But this is because, well, we can do it really for any function, right? If we can evaluate a function at any point, then we're good. We can compute a derivative, right? I mean, we just run the input through the function and get the result, and that's it. That's easy. If you can create the output, you can compute a derivative. But maybe you want to have something better. So we want to have a function that actually computes a derivative of any function. So we want the function capital D, which, when it's given a differentiable function, so differentiable function means you can compute derivative for this function, right? So differentiable function from R to R produces another function from R to R such that, okay, well, it's a terrible definition here, such that for n input c, the function gives me the derivative of the previous one. So what does it mean? Do you have an example? Yes, no. Okay. I want a function that I just plug in here C, and it will give me this kind of computation of the overall limit. So I want to make things simple. I'll give you an example of what it is later on. So let me see. So with the derivative computing function, d is written as d over dx, or other also notations like d over dx f. So this is not a fraction. This is the name of the function, right? So don't confuse it with a fraction. It's just a notation. Or df over dx, or dy over dx. So this is something very nested. And if you use this, you have to choose what is x and y, and you might not have even x and y. So here, something like a first warning, the notation is so there's several notations of how to do this derivative computing function. But an example, okay, so if we have fx equals, let's say, x squared, what is my function g in this example? Yes? 2x, yeah, that would be 2x. We don't have x here, we have c, so it very correctly would be like 2c, because for every input c, we get the derivative of this function, but typically we don't switch variables, so we would say it's 2x. And that's what you learn, or the rules of derivatives at high school or in calculus, right? So there is no brainer, but it has a name, and then you have different notations for this derivative computed function. At any point c, you get the derivative evaluated for this function f. Okay? Any questions? Nice. So then we have something where, so we are talking about the nested function or the function composition with the circle in between. So if we have a composed function, which is first f, and then the output goes to g, there is a rule. You might know it under the name of chain rule or other names. Do you know other names for this thing? I know it as a chain rule. Okay, chain rule. Kettenregel. That's a chain rule to me. Okay, good. Which is telling you if you have this composite function, how do you get a derivative of this function? So how do you get, let's say this is, and now we can, how do we write a derivative function? So we might write dg dx, or we might say dy over dx, right? This is the same thing, because here we implicitly assume this is going to be equals to y. Here we putting the name of the function in here. Okay, it's getting complicated. Or g prime of x may be possible. Anyway, so you have multiple ways to write the same thing. And we're mixing up here. We're not programming, we're using mathematics. So, it won't compile, but you get a gist what it means. It won't compile because here it's a function, here it's a variable of, oh my God. But anyway, the rule says that you take first, it's a theorem, so you can prove it, but it says first you evaluate your inner function f and plug it into a derivative of function g and multiply it by the derivative of the inner function at the point x. Okay, so this is a chain rule. You might want to remember that. Okay, yeah, here's another way to write this. If we have this circle composition operator, this is the same thing. So again, we have two functions which are derivatives, and now we're saying, okay, this is a composition of these two, which is very equivalent to this one. So then the derivative of h is h prime, which is this sort of. It's the very same notation, but sorry, the very same meaning, but different notation. So you take the output of f and plug it into derivative of g and multiply by derivative of f. This is the same story, but just written differently. So that you're aware of that. If you ever see something like that in libraries for differentiation, then you understand that what it means. I think it's like there's multiple variants, or it's like a language, and you can say it in multiple. It's like the underlying intuition is the same, but you have multiple languages talking about the same thing, right? So the first one was English, this is Spanish, and now it's coming German because it's Leibniz notation. It's the same thing. So again, we have a combination of functions, and then we're using this Leibniz notation, where dh over dx is the derivative of h, then the chain rule is dh over dx, it's dh over df times df over dx. This is very tricky. This might be very tricky because if you look at this as two fractions, you are kind of urged to say, oh yeah, I'm just multiply these two fractions. Oh, okay, yeah, that works. No, that's wrong. I mean, conceptually, this is wrong. You can't do that. I mean, you can do that on paper, and you get the result, so to say, but it's not how it works internally. It's just that, you know, the notation kind of shows you the chain rule, how it will look like. If you have like multiple derivatives, then you can just take it as a multiplication of fractions, but that's wrong, you know. So don't do it. I mean, this is just the way it's written, and it kind of might be easy to show this, but it's not a fraction. Okay? Any questions? All right. So I hope you're still with me. So we know how to do the, okay, so we know what a derivative is, right? We know what is if you have composition of multiple functions, we know how to do the chain rule now. So you can nesting functions, but it's still error to error. I mean, this is still one variable input, one variable output. But this is great. So, okay, here's one chain rule example. And I guess this is kind of interesting to show like the different notations here. So if we have this function, y equals to e power sinus of x squared. Okay, so it's a composite of three functions. So the inner one, and we put here arbitrarily the names. So we just made it up. H and v, we just made it up. So h is the inner function is h, which is x squared. Then we take the sinus of this v, which is sinus x squared. So this is the other function, and the main sort of function is the exponent. So the Euler's number x of. So you can write it also as a exp of u. Okay, what is the definition of this function, by the way? What is exp? How do you define that? How do you compute it? Yes.
We can take the usual power series definition.
Yeah, okay, you can use the power series definition. So like k from 0 to infinity, and I guess it was x power k over k factorial is one definition, for instance. Okay, so this is this function, and if you plug it an exp of 1 equals the letter e, which is the Euler's number 2.71 something like that. Okay, so this is the e function, and it has nice properties, as we'll just see in the next slide. You don't have to remember this. This is just it's a function. E of something is a function. Okay, so we have these three function composed, and then let's take a derivative of this whole thing. So we're interested now in dy with respect to x, okay, of this function f. This is what we want to compute. And we're going to use a chain rule because we composed already the function to three parts. So we look in each of these functions in isolation and compute the derivatives of them. This is what we're gonna use. So let's start with the e to u, and this is beautiful. So derivative of this function is the same function. It's so you know, ex derivative is again ex. Okay, this is the nice thing about exponential function. So we're gonna end up with EU, which is, again, we plug in the u from here, and this is going to give us this thing. Okay, so then the derivative of the second one, of the sinus, yeah, you might or might not remember. You can look it up on Wikipedia. So it's cosinus, right? I mean, this one I remember, this one I always forget. So, but cosinus is the derivative of sinus. And here again, we plug in the v and get this derivative of the second function. And then derivative of x squared we had already, so it's 2x. Okay. So any questions to that? It's should be self-explaining after what we've seen, but maybe there's something confusing still about it. So crystal clear? Good. So we have this thing, these derivatives, and then okay, this is the recapitulation again, and what we're gonna do with them is to use the chain rule, which is just a multiplication of these three things, right? In this Leibniz notation, which we saw 3 slides back, we're going to multiply these three derivatives together, which will give us, let me see if there's a result. No, so it will give us, the derivative will be, this rule will be x sinus x squared times cosinus x squared times 2x is the dy to dx evaluated at x. Okay, or any other point, x maybe a, right? So this is the chain rule in praxis. Like you compute the derivatives of each of the individual functions because you can do it very easily. You know it, like derivative of x squared is 2x, derivative of sinus is cosinus, derivative of e is e, and then you just stick them together. Okay? This is the chain rule, so this is easy. And again, what you see here is that you're using the computations from the previous into the next one. So you're using here, let me see, x squared. You're using the output of the previous function in the next function. So for example, this function was x squared, and using the output of this x squared in the next derivative, and you're using the sinus x squared in the parent function as well. So this is also chaining the results. All right, so everybody's happy? Good. All right, so now we know how to use chain. Okay, so derivatives, functions, chain rule. And the goal was to, okay, so finding a minimum of function. So we want to find x here that gives us a minimum of the fx, okay? So again, we can evaluate fx at any point. And now we can also, let's say, we can do that. We can evaluate its derivative, f prime c, or this kind of notation, Leibniz notation, or Lagrange notation for any c. So we can do that, which means we can evaluate if we have this function, for example, we can evaluate, which means give the result of the function for any x, and we know how to compute the derivative of this function for any f, for any c. Okay, we can do that now. We have the chain rule, and we have the function which we can evaluate. Okay, so let's try to find a minimum of this function. How to do that? So how do you find a minimum of this function? If you don't know the function, I mean, you know, if I ask you like, where's the minimum, you just look at the function and say, oh, well, it's right here. Yeah, because you see the whole function as as a human, and you perceive it, right? But it's a very simple function, and you can't answer. I just look at it, because as a machine or whatever algorithm, you don't see any function. You know how to compute it. You know how to compute the derivative of it, but you don't know how it looks like in a way, right? And you want to find a minimum. So we'll use, it's called gradient-based optimization, as we'll see later why it's called gradient. So now you can ignore that. But we'll start with some sort of initial random value. Okay, so let's pick a nice initial random value, and maybe we'll start here. Okay, we'll start here. So, and now, so this will be like first point x1. Okay, x1. We evaluate the gradient at this point. So we take the function here, we evaluate the gradient. So gradient is kind of, sorry, gradient, the derivative of the function. And as we saw, the derivative of the function is basically the slope of the curve here. So this is the derivative. And now we know the derivative. So the line is just saying, no, we're not using the line actually, we just use the derivative. So here the derivative will be something which is a positive, right? Because it's the slope of this function will be a positive number. So the direction and strength of change at xi, right? So this is this sort of function, and it has some slope, and it's like middle steep, I would say. I don't know. I mean, I can't describe like the steepness, but it's sort of okay steep. So it will be some positive number, okay? So I'm just deleting the line. So here we have a positive number for this u. And now we're gonna move somewhere else to the next, to x2, where we take this positive number. We'll use some constant, some other parameter, which is called the learning value, or sorry, learning rate, some small eta thing. And we're gonna subtract this number from the current one. So if here the u was positive, and we multiply by some small positive number, we'll get some positive number. So here, x1 minus some positive number will move us where? To the left or to the right? So who thinks is going to move us to the left and who thinks is going to move us to the right? So left. Okay, good. Right? Nice. You're right. You're correct. It's going to be to the left. So we're now moving somehow. We don't know how much, because we didn't specify the eta, right? It could be quite a lot or quite a bit. Let's say it's quite a bit. So it moved us quite a bit to the left, and here we have x2. And repeat. So again, evaluate the direction and strength of change at this point. Okay, here again it's gonna be a line. Maybe it's gonna be this slope. Okay, so it's gonna be a positive number. And again, we're subtracting the positive number times the learning rate, and we're gonna move again to left somehow, somewhere else, maybe here. Okay. Oh, cool. So now repeat. Again, make a derivative. So it's gonna be looking like that, maybe. So it's gonna be a negative slope now, right? We're going on the other direction. So it's gonna be y is minus something times x. Oops. So it's going to be negative. And which means we're now moving our point not to the left anymore, but we just, minus and minus is plus. So we're going now to the right. And by repeating this and choosing wisely the eta, we will end up maybe in this minimum or maybe somewhere around. Okay. So what is the derivative is telling us? What is its role? It's saying two things. It's saying the direction where we need to move next. I mean, the derivative is saying like the direction and of the change at y. So it's saying if you're here, the derivative is saying, well, the function grows on the right hand side, right? So it's saying like where we need to move to the next lower point. And what's the steepness of the function in there? So we're using this for moving very wisely. I mean, you can minimize a function in many different ways. You can just randomly pick a point and do randomly. I mean, minimizing a function. If you have this, you can just say, okay, what's the minimum? I don't know. Let's pick randomly this. Okay, why not? It's good. So this is my point x1. Okay, let's pick something else, some random point. Okay, cool, random point here. Oh, it's still not smaller. Let's pick another random point here, a random point here, and you repeat it like 100 times, and you get some minimum somewhere. You can do that, but it doesn't guarantee you anything. It could be random. It's not, but it might work. You might be lucky and end up with a minimum or not. So it's a random guessing is also a way to minimize a function. You can just pick a random point, or you can just, if you have just 1D function, you can just take every point here, very small, and evaluate all of them, and then just pick the minimum. You can do that as well. It will work for simple functions and small range, but it's kind of stupid because you don't take into account what you know about the function, which is it has derivatives. And you can use the derivatives to kind of tell you if you're at a certain point where you need to go to have something smaller. This is the point. If your learning rate is small, there is some sort of guarantee that the next point will be smaller than the current one. Will you end up in a global minimum or a local minimum? It depends on many things. Depends on the function, on the learning rate, and stuff like that, right? But there's at least some guarantee that whatever you do next won't be that stupid. It's better than just random guessing. It's going to be smaller because you're using the gradient and the point, okay? Any questions? I'll ask a question. So can you now minimize a function of one variable? So can you do that? Could you implement it? So again, what do you need for that? What do you need to implement minimizing a function? You need to compute what? Two things. First and second. Yeah, you are first. The derivative of what? The derivative of the function you try to minimize for any input point at any point. right? This is important. Like, yes, it's kind of implicit, but you know, explicitly you need to know the value of the derivative of the function at any point, basically, which tells you what is the slope of the tangent at any point of this function, right? So this is what you need. And the second?
That's mostly open. You just need to code step 1 to 4.
Yeah.
And some way to express functions.
And you well, yeah, I mean, it's kind of implicit in you. If you can compute derivative of any function, for example, this one, like 3 minus sinus 2x over x. So you need to evaluate. So the two things is you need to be able to evaluate this function for any x, which is easy. You just write in Python 3 minus whatever np. You don't need numpy. I guess in math is sinus 2 times x over, this is it. So this is the first step, and you can evaluate the function. And then, okay, well, how do I compute the derivative? Well, I'm gonna use the chain rule. And if you're gonna code up the chain rule, I mean, you can do it by hand. You know, the derivative of that would be what? Okay, so this goes away. This is -1, so -1. Then a fraction. So you can use some rules for product of. So product rule is also something you might use. I mean, you can, after 5 minutes, you end up with derivative of that. But the chain rule makes it much easier because you just follow the simple rules and make it, every tiny little function and then compose them together. So maybe I would do, I mean, what you do per hand is basically also like a chain rule, but not explicitly. So you can code it up, and then you know how to do the derivatives and how to have the function, and then you call it a day and just implement this algorithm. So now you should be actually, I think you should really be able to compute a derivative or finding a minimum of any function in R. You have a question? I can't see that. Can you just show me again?
And then going down, but not exactly, just going to some point to infinity, and just.
Oh, okay. So you want to minimize a function which is something like that, and then it goes to infinity like that.
What if you on the left could have a different one?
Okay.
And then it kind of.
So like that, and that.
No. The idea is that the minimum.
Can you come? Okay, come here. You don't mind if you be on YouTube? Is it fine? You won't. Okay.
Right, thank you. So the idea is that if we have a function.
Yeah, just close. Okay.
All right.
No,
Where we go down quite a lot, and then just go to some kind of axis that is above this.
Oh, okay.
Oops, sorry. And if we start here, we will go down to infinity there.
Yeah.
Although here would be a minimum.
I see.
And that's like problem.
Yeah. Thank you. Yeah, that's correct. That's a problem. So exactly. Well, why? Where's the hack here in this algorithm? Why this is going to fail? If we have this sort of function, so okay, let me just make it clear. We get like that. So the minimum is here, but what if we start here? So where the algorithm is going to end up? Yeah, because here it says, okay, we need to go next here, and next here, and next here, and you're doomed. Yeah. So
we saw this scenario before. This is just we have two minimums, or in this case, one well that we can reach the minimum of, but
well, okay, I see. Well, we have one global minimum actually, which is here. So we would love to end up here, but we end up somewhere else. So where's the problem? What is the problem of this algorithm here?
It only finds a minimum, not the global minimum.
Sure. Yeah, I mean, this is a feature of this algorithm, but not a problem. Like, well, okay, I see your point. Okay, you're right. So it finds a minimum, not the minimum. And this particle problem here, well, like what went wrong here? What went wrong? Why didn't we find this minimum we were looking for? We started here and we didn't find it. Why? Just maybe someone else. Maybe someone else. Why we end up so badly here in this example? Where's the problem here? Where's the catch? I'm sorry. No, sorry. Yes, I would. Exactly. Yes. We started with the random value, and the random value was just wrong, you know, in a way. I mean, we start randomly. We said, yeah, let's start here. Yeah, and it fails, obviously. If we started here, we're lucky, or here, right? Given like good enough eta, then we would end up with this minimum. So it's prone to this random initialization. Whenever you start, it will lead you there. Like if you have sort of different functions which are very complicated, yeah. So it really depends in which kind of value you start your journey. You'll find a minimum all the time. But if you start here, you find this minimum. If you start here, you find this, and so on. But it's like randomly dropping you somewhere in this function kind of determines where you end up. So you might want to do like multiple initializations, you know, if you can afford it, where you just basically start it multiple times for multiple very random values, and you just see, you know, which one gets you the minimum. Okay. So does it answer your question? Like, where? No, this is a nice problem. Like, yeah, this is bad. Is it really bad in practice in deep learning models for NLP, like where we have not a global minimum but a local minimum? It turns out that's not the case actually, and there's a reason why is it so. I mean, we'll see later. Okay, but just purely sort of mathematically or algorithmically, finding a minimum of the function has different caveats, like this one, the random initialization. But you should be able to implement it. Okay, any other question? Okay. So we worked out through this example. Okay, so as I said, like whenever you start, then you will end up somewhere. Now, before we make a break, so the question is like, shall we make a break now or maybe in 15 minutes? So let's go for 15 minutes and take a break, because then everybody needs coffee. Okay. So we're talking about functions in 1D, which is nice and simple. The derivative is telling you go left or go right. That's easy, right? I mean, okay. You can even like compute basically another solution. Like you don't even need the derivative. If you're at this point, you can say, okay, let's take something plus and something minus and compute those two and just compare. And which one is smaller, then go there. You can do that as well. You don't need a derivative for that, because it's a little information in 1D. The trick is if you come to 2 dimensions or multiple dimensions even, things are getting trickier. So you don't want to use this sort of naive solution. You need really a derivative, because functions are, you know, the surface gets more kind of well, larger, so to say. So multivariate functions means we have n dimensions, so the function is from n dimensions to real number. Okay, so here's an example of a 3D function. I don't know if you can see it. It's like a banana shape, right? So it's a valley, and there's a banana valley in there between the mountains. And this is how the function is computed. It is a name. Anybody saw this function before? Okay, that's fine. You don't have to know that. It's a Rosenbrock function. And it's famous in function minimization because this one is really hard to sort of minimize for some reasons. You know, it's tricky. So the minimum is of this function. I hope I have it on the next slide. The minimum of this function is somewhere here in this valley, exactly at one point. But it's a tricky to get there with the methods we're using. So banana. Okay, why banana function, Rosenbrock. Anyway. So this is one example of the function which we might want to find a minimum, so minimize the function, and we want to find this spot. And here the minimum is exactly, you know, you can calculate it pretty exactly. So now, okay, so we know how to make a derivative in one-dimensional function, how to make derivatives in multivariate functions, and here we come to partial derivatives. So we have always previously derivative with respect to one variable. Now we can make derivatives with respect to multiple variables. So, and it's called partial derivatives. So who hasn't heard of partial derivatives before? Okay, good. So this is great. So we have, how how to compute that is actually pretty much the same as in derivatives for the single variable function. So the terminology is this sort of this thing which we call partial. I don't know if it's a name like by itself, the symbol, but this is this symbol, and it's telling the partial derivative of f with respect to x2. Okay, this is nice because it's telling like what the function we have a function and we want to make a derivative with respect to a particular variable. So if we have a function, here's an example. We have a function of 3 variables, x1, x2, x3, and here's how the function looks like. So x1 squared times x2 plus cosinus x3. So how do we make now? I mean, you have the solution here, so it's not fun anymore to do it per hand. But anyway, how would you compute the partial derivative of f with respect to x1? And I guess this is what you learned before, is that you take x2 and x3, all the other variables, as a constant for this part of your computation, right? So if you want to do f1 with respect to f with respect to x1, it's this, so this will be a constant, and this would be a constant. Okay, this is easy. So this is a constant, derivative is 0, and then you have, okay, x2 times derivative of that is 2 times x1. Okay, so this is the derivative. So everybody knows how to do partial derivatives per hand? Okay, good. We don't have to do it per hand at all in whatever you're doing. So you're a little puzzled. Does it make sense what you're doing?
No.
Okay, so for example, partial derivative of with respect to x2 is that this is constant and this is constant. So derivative of this is 0, and derivative of constant times x2 is, so what is the derivative of function? What is now, okay, let's make it simple. What is x squared times c? What's the derivative? Sorry, wrong. No. What is a derivative? Sorry, what is a derivative of c times x? What is the derivative of c times x? C, exactly. So here, this is c, and this is our x, so the derivative of that will be just c. Okay, so now it should make sense for you as well. Does it?
The problem is not for it to make sense. The problem is sometimes the language, because I knew math only in German, and sometimes I have to think about what it means.
Ah, okay, yeah. Oh, yeah. Sorry. Okay, I don't know anything about math in German. I would be.
Website where I can just.
I would be so horrible in that. Kettenregel, I could kind of relate. How is derivative? Derivative? Ableitung. Wow, and partial derivative? Partielle Ableitung. Okay, actually, I watched. Okay, so last night I watched one YouTube video on something with, I don't know, like measure theory, something like that. And the guy was German, obviously from his accent. So it was in English, and then I switched to the German version, and it sounded really funny, like all this terminology, like mass theory, and all these terms. You know, this is. I mean, if you're not familiar with these terms, I mean, this is kind of. So I understand your point. Okay, so if you never saw mathematics from the English speaking perspective, then might be confusing. Okay. All right. But like, does it make sense? Good. Okay. So we have partial derivatives. Okay, so we know how to do partial derivatives of function with multiple variables. This is great. Then we have a thing called gradient, which is so again, this is the example from the previous slide again. So we know how to do partial derivatives of with respect to each variable. So the result of a partial derivative with respect to each variable gives us something which we call, it could be a vector or a matrix, which is called the gradient of f, and we use this symbol. Do you know the name of this symbol? It's nabla. But we call it gradient symbol. So nabla, the gradient symbol. And here an example. Okay, again, this function, and the gradient for us is a vector of partial derivatives. So for each variable, it's just a vector of partial derivatives. Okay. And here we computed these partial derivatives before. So this is a vector of partial derivative with respect to x1 is here, with respect to x2 is here, and with respect to x3 is here. So this is the gradient. And what is the gradient saying? Let me see if I have an example. Yeah. Okay, so this is a definition of the gradient. Any questions? How's gradient in German? Is this? Okay, gradient. Cool. So we have gradient. We have the gradient, and it's a vector of partial derivatives. So what are the gradient? What are the properties of gradient? So here's the example again. We have this function, and this is the gradient. So the gradient for every differential of the function from n dimensions and every point here, which we plug here, the gradient. So if we take a point and plug it in here and evaluate it for each of the point, we get 3 numbers, right? We get a vector. The gradient points in the direction of the steepest ascent of the function at x. So what does it mean? If we, for example, have I'm coming to this function. So if we have the gradient maybe here, if we compute the gradient for this function here, we get a vector which might be pointing somewhere towards the hill here. If we evaluate the gradient here, we might end up with a vector which is pointing here in this towards the other hill. If we have a vector here, the gradient, it might be pointing, I guess in this banana function, it goes like that, right? So it's always pointing you to this more, to the steepest hike you can take. Basically, the analogy in 2 dimensions, if you're in the mountains, you're somewhere and you just look, where do I go? The steepest here, this is the gradient. Basically, this is the direction of where you can go. Well, it's not pointing like if you have 2 dimensions, it's not pointing up, it's basically telling you the direction, right? So it should be, sorry, this is actually wrong. It should be like, it shows this direction and it shows this direction. No, it doesn't go up, basically just a two-dimensional vector. So it's in 2D, right? But it's showing you the direction where it's steepest. Does it make sense? Okay, gradient evaluated at any point shows you the direction of the steepest growth of the function. So, and again, like a little notation chaos. So sometimes we call the gradient the function which is computing the gradient, and sometimes we call the gradient the actual vector of the values. Sometimes we call this a gradient. So just beware, if you tell gradient, it could be multiple things. So this is how you compute the actual gradient for a point for a given x. So this is just a terminology, okay? So this is the gradient, okay? Shall we make a break? Let me just, yeah, we'll finish in 4 minutes and then we go for coffee, okay? So we have a gradient. Now we want to minimize functions again, but now we want to minimize multivariable functions, so like the banana function. And again, well, we use the same thing as we had before. We just extend it to multiple dimensions. So we again want to find a point where we have the minimum. So if we had the banana function, we want to find the valley, like where's this, the lowest point on the valley. So again, we start at random position with a random value, but now it's multiple dimensions. So we have a vector, a point somewhere, multi-dimensional. So we have a point somewhere in this maybe 2 dimensions. We start somewhere in the mountains. Then we compute the gradient. So this is the actual value at this point. So it's here by gradient, I mean this particular vector of values at this point. And again, so this is the gradient. And we have this eta, the learning rate again. So we subtract the gradient multiplied by this learning rate and move somewhere in the opposite direction. Okay, what does it mean? So if you're in the mountains and look around, like, okay, where is the steepest extent? Okay, it's this direction. And if you're gonna go up, you go the opposite direction exactly. This is the steepest descent, basically, like, it really goes uphill here. So this is why there is a minus again. And you go the opposite direction if you want to minimize your function. It's pretty. I think like this analogy is pretty correct actually. So you go downhill, but you're blind. That's the point. You don't see where the mountains are. You're blind. You just know that the gradient. So you go opposite. A couple of steps, and then you say, okay, Where's the gradient now pointing? Okay, it's maybe the same direction, maybe a little bit. Okay, so I'm going the other side, and you make a couple of steps. If you know the gradient at every point, then you should end up somewhere in global minimum or local minimum. Sorry, mostly local minimum. And after enough iterations, we found something which should be some minimum of the function. Okay, so this is the very same algorithm, and it has a very same issues as the previous one. Like you start with a random position. So depending on your random sort of initialization where you start, it will kind of show you where you end up. You know, if you're, do you know? Okay, off the record. Like, have you watched Bear Grylls? Do you know Bear Grylls? So he was. So there was some. So this is serious about like survival guy. I mean, ex-soldier in the UK or something like that. And he had a show, and he was left somewhere in the middle of nowhere, maybe in the mountains, you know, from a helicopter. So he just jumps out of the helicopter and tries to survive. And so he's randomly dropped off somewhere, and then he goes just uphill and try to find water and, you know, civilization in 3 days. And it's a funny show, basically. It's not real survival. But it's really depending when you start, you know, when your helicopter lets you off in the mountains, well, you know, it kind of makes your day good or better, you know, depending on how far or where you start, then you will see how far you get. Okay, and it's a nice analogy, I guess. Okay, so that's what we have. So random positioning really matters. But the rest of the algorithm is the same as in one dimension. So here, for this function, if you take a partial derivatives, I mean, you can try home, take the partial derivatives with respect to x and with respect to y, and you end up with a vector of two sort of. So this is the derivative computing function, and if you plug any point here, you get exactly the steepest ascent at any point. Okay, so this is what you get for this Rosenberg function. You can really compute it by hand, this sort of function. And then let me see what's here. Here's an example where we started at this point. So this is like a satellite image view, right? So this is the valley, this is the banana, and the minimum is actually somewhere here, 1, 1. So this is the actual minimum of this function, but we use this iterative minimizing function, and we started here. So here the gradient was pointing to the steepest ascent, which was like that. So this was the gradient somehow pointing. So we took the opposite direction and went to this point. Okay, here at this point, the gradient was pointing uphill, so like that. So we take a step here, and here the gradient was pointing here, so we take an opposite step, and here the gradient was pointing here. We took an opposite step, and the gradient was here. But here the gradient is getting smaller, right? Because the steepness is not so huge. I mean, it's already flat almost in this valley. Does it make sense? So here the gradient was super steep, like we're here and it's like very up, you know, it's like steep mountain. So that's why we took this big step, big step. And here the steps are getting smaller because the gradient is getting smaller. And after 100 iterations, our algorithm decides, okay, that's enough. We found a minimum because I don't want to repeat it for infinity. Well, the actual minimum was much farther. So that's also like one decision of this algorithm is like you have to stop somewhere after enough iterations, right? So maybe you say, well, I do just 1,000 iterations and then I stop, which doesn't guarantee again that you find a minimum. Maybe you're on a good way, but you just say like, let's stop here. I don't want to do it forever. So this is how it works. 894 iterations for that. Any questions? So we had this naive approach, like, well, you find a minimum by just sampling, you know, random points or just to look left and right. You can't do that in 2 dimensions that easily, because if you're here, you would need to compute maybe like 100 points from your old neighborhood and then pick one. So it doesn't make any sense. Like here in these 2 dimensions, you wouldn't do that. You need a gradient. This is like much faster. You know where to go exactly. One computation. So this is why random sampling or some naive things won't get you anywhere. Okay. Any questions? So we know what is a derivative of a function. in partial derivatives of multiple dimensions, we know what the gradient is doing, and we know how to use it for minimizing functions in multiple dimensions. It's cool, isn't it? I mean, you should be able now to program this actually, like this Rosenberg function. You should do that. It's and you find exactly how you end up, how the trickiness of the random initialization are, and how many steps you need to find a minimum. Okay. Any questions? Then let's make a break for 9 minutes and start 9:30 and finish them. Okay. Cool. Okay. So, let's see. Okay, so minimizing functions. Okay, good. Yes, so we know how to minimize functions, and now basically you should be able to build something for minimizing some training error. Now you are equipped with everything to be able to implement it, but things are not as easy as it might look. So we had some, well, I mean, like this is not a nice function, but it's still doable per hand. I mean, you can still compute the partial derivatives per hand if you try hard enough and play around with derivatives, because there's rules you can apply, and you end up with this for some after some effort. But what if you have some very nasty, heavily nested multivariable functions like this one? So for example, we have this function e. Well, this is not the Euler constant, this is just a variable e. And we have k parameters or k inputs, and this is how the function looks like. So it's an average of a sum over logarithm of something over something, exponent of some other sum times this thing. This is a very nasty function. Like for, can you do a partial derivative of this function? Can you do dE with respect to dW0 on paper? Well, you could theoretically. I mean, you can really play around with that, and you will find all these partial derivatives per hand if you really try hard. But what if you change a little bit your function and just delete this? How this will change? Yeah, so okay, maybe not that much in this case, but maybe you just remove one of these parameters, maybe W1, so it will change pretty much a lot of stuff. So you need to do per hand. Okay. So maybe definitely there's a better hand how to compute derivatives of this complicated function. So we're gonna use what? We're gonna use a chain rule for computing this nested function derivations, right? So chain rule helps you to do derivative of a complicated nested function, as we saw before, this e to sinus, cosinus, and stuff like that. There's no difference between this and the other function, although this is more complicated. But maybe there's a better way. So we need this, okay? So we need to find the gradient so that we can compute for any input, we can compute the gradient value for this function, right? And we need these partial derivatives, but that's what I said, like good luck with computing this per hand, okay? So again, why we need this gradient? Again, what we're trying to do, what's the main goal? Sanity check, if you're awake.
We are looking at minimizing the function.
Minimizing functions.
Gradient.
Exactly. Minimizing functions. Okay, exactly. So we have chain rule. Okay, so we had chain rule for single variable functions, but we have chain rule for multivariable functions as well. And here's I don't think you need to remember this, but this is just how you compute it. It's the very same thing as so we have two functions, and now we again I have different naming. So S is a function G of some input T, and Y is a function H of some input T. So there are two functions of T, G and H are differentiable, and there's a composition of these functions. So it takes X and Y together. So let's have it like that. So X is a function, Y is a function, and they go to Z is a function, and they depend on some T. Okay, so like that, like graphically, I would visualize that. So then the partial derivative of Z with respect to T is partial derivative of Z with respect to X times derivative of X with respect to T. Okay, so this is basically chain rule this way, plus, so this is one path of the chain rule, plus chain rule, so derivative of z with respect to e. So here times the derivative of, sorry, e, y. Derivative of z with respect to y and derivative of y with respect to t. So chain rule on the other part. And we sum them up together. Okay, so this is how you compute so if you have multiple paths, like previously we had only one path. So we had like x went to y, x went to z. So this is like easy, like this, there's one chain basically. Here you might have multiple chains, you sum them up for multivariable functions. Okay, does it make sense? So if you had like multiple paths, you sum them all together. It's a theorem basically, and you can prove it. Why is it so? But you can take it as a fact. Okay. And again, so here we're mixing up the partial derivatives and we're mixing up the standard d derivatives, but also you might use just the partial derivatives all the way down. So, you know, the notation is kind of tricky here. Again, just, you know, you should know what it means under hood, and the notation is just a language how you express the things. So I guess this is using partial derivatives everywhere makes a lot of sense because it's just multivariable function, partial derivatives, it's fine. But, you know, you might also see this kind of in some sources. Okay, and then if we have two independent variables, okay, so we have a function g of u and v. Okay, so we have function g of u and v. So this goes here, and this goes here. Differentiable, and we have, oh, sorry. Yeah, this is it. So again, the notation is horrible. So x equals to g of u and v, and then y equals to h of u and v. So we have two functions, h and g. And then we have another function, z equals to f of those two. Right? So this is how we compose the function. So we have multiple variables here as input to these two functions, and then we have one function which takes these two together. Then here's how you compute the partial derivatives. Oh, and basically this is the same thing. So the partial derivative of z with respect to u, so the partial derivative of z with respect to u is partial derivative of z with respect to x, okay, makes sense, times partial derivative x with respect to u. Okay, so this is a chain rule again, this, nice, plus partial derivative z with respect to y, okay, times partial derivatives y with respect to u. Okay, so this is the same thing we had before. There's no difference, like, oops, where's that? This is the same thing as with one variable. So we did it just for the u. And now the partial derivative of the other input for a v, colors, let me use colors, is partial derivative of z with respect to x, okay, makes sense. So this is this. And then partial derivative x with respect to v. Okay, yeah, makes sense. Okay. And then plus the other path. So partial derivative z with respect to y. Okay. Times partial derivative y with respect to v. Yeah, okay. So we have basically covered all variables with all different paths and summed them up. This is the multivariable, the chain of rule for multivariable functions. And this is all you need for computations of derivatives of nested functions with just multiple variables. Okay, so any questions? Not really. You're not convinced. Say again?
I'm just not good with theory.
This is not a theory, basically. This is how you do things. I mean, this is. Oh no, I mean, don't get me wrong. I mean, I understand. Maybe I understand what you mean. So you don't like, this kind of theoretical things and how you express that stuff like mathematically. You learn by examples. That's great. We'll have an example, but this is the underlying stuff that kind of governs the examples later on, right? So if this doesn't make sense yet, it should make sense after we have this example. And after you see the example, you should come back and see, yeah, this is just a simple rule, and I know why. Okay. but it wouldn't make sense to start with an example because you would be using on this formula and like, where does it come from? You know? So it's better to show everything like up front and saying like, we're going to use a chain of, the chain rule for multivariable calculus, and there's just two operations. We take all the paths, multiply all the pieces of the chain together, and all the paths which lead to me variable which I want to take derivative, I'm just sum them up. That's what the rule is saying, with this very inconvenient notation with partial derivatives and blah blah blah. But basically, it's saying, okay, I'll take this path and this path to get a derivative of this with respect to v plus the other path. If I had multiple variables here, multiple intermediate functions, gh, l, something, I would go here and so on and multiply them together and sum up together. That's it. Okay. So, any other question? No. So let's do it. So let's have a working example now. It's a function of, okay, so let me just come back to blue. Where's my blue? Here? Yeah. Okay. So we have a function, this function, which is a and b are the input variables. This is a constant, and e is the output. I call it e, something like error, because it might be error of the training later on. So that's not by chance, but it could be y, whatever. This is just an arbitrary decision of naming things. So e is a plus b times b plus 1, and I want to compute gradient with respect to a and b. So what does it mean? I want to do partial derivative of e with respect to a, and I want a partial derivative of e with respect to b, and this is going to be my gradient. That's what I want. Okay, I want to know, because if this function is the banana function, whatever. So for instance, if this is where the banana function, I want to know in every point what's my steepest direction, because I want to take the opposite direction. This is why I want the gradient all the time. I'm interested in gradient because I want to see where should I go next to minimize this function. Okay, so that's what I want. And actually, you can do this easily per hand. Actually, you can really have this gradient computed per hand, because this is going to be these two functions. You can do it easily in this case. This is not a complicated function, but that's not the point. The point is that's easy enough to show the algorithmic tools to compute a gradient efficiently. Okay, so this is our working example, is this function. Everybody's with me? Good. So what we're gonna do is we'll add some, let's say, intermediate variables and function names to make it really clear. So the e we had before, so we call this, okay, e is the variable name, so this is what's coming out. We call this function f of r and s, right? So this is what I decided. So this will be r, this will be s, and we have a multiplication between. So f1 equals r times s. So this is multiplication of two things. Okay, this is simplifying the notations, making it very explicit for each of this computation. So what is my r then? R is, I'll call it f2. R is going to be a plus b. Okay, good. Yeah, makes sense. A plus b. And my s, which is a variable name, it's function 3 of b is going to be b plus 1. Yeah, I'm just making explicit what's implicit in this notation here. Just make it very clear. Why? Because let me just because I want to build something which is called a computational graph. So what is my computational graph? Is that the nodes are functions or inputs. Okay, so I'm using here the orange ones are the inputs, and these oval ones are functions. And this is basically just showing exactly the composition of the function, right? So you see the parallel here. So I have f3, for example, is here, which is takes an input of b, right? And b is here the input variable. And here's how it's computed. So I mean, I'm not putting this here. I'm just using the s equals to f3. So this is the function definition. Okay. So And AB will be some concrete real numbers. And that's why R, S, and later E will also be some concrete numbers, right? I mean, if you plug something in as a function, like A will be 2 and B will be 4, you end up with some number 14 or something like that. I don't know, right? So these will be concrete numbers. And this computational graph shows me the dependencies of each function of these of the previous functions. Okay. Have you seen like computational graph before in other contexts? Maybe yes, maybe no, doesn't matter. It's an abstraction basically, but it helps us to really see the how can we simplify things to make them efficiently computable. Okay. So so the computational graph is DAG, so direct acyclic graph. It doesn't have to be a tree. So this is not a tree. This is just a graph. Did you have a graph theory or something like that? Do you know what a graph is? Okay, cool. So it's a graph, it's not a tree, and each node is each node is a function, and we kind of assume it's a differentiable function. And it has some arguments, okay? So what does it mean, differentiable function? Well, I can take this function, for example, R, and I can compute a gradient with respect to the input. So I can take, for example, R with respect to A, or I can compute R with respect to B. So this is what I'm assuming each of these nodes is differentiable. And these are input nodes. So, so these are the leaves. The leaves are variables. So these are constants, and I'm using them for computation. And the arrows basically show me exactly the composition of the function, right? So it's just very graphically explained. What else? Parents. So R and S are parents of B. Okay, so terminology, parents. A and B, and parents. So R is parent of A and B, and S is parent of B. Okay, and children's as well. So this is like a standard kind of notation. Okay, any questions so far? Good. So what I want to do, okay, let's zoom out. I have this function, and I want to compute the gradient. So I want the partial derivative E with respect to A and partial derivative of E with respect to B. So I'm going to do like iterative algorithm on this graph in order to compute those things. This is our goal. And I'm going to compute partial derivative for every node. Okay, so I'm going to do that. Okay, so why? You will see later because we're using a lot of things. So we're gonna reuse, if we compute this derivative, partial derivative for all of the nodes, it's gonna make computing the gradient of the output much easier or faster. So I'm starting here at E. So I'm starting at the output of this graph. So okay, how many outputs, how many sort of sync nodes does this graph have? Like any computational graph, how many outputs would be there?
We're looking at scalar functions, we only have one.
Just one, exactly. We are computing just a single number. So it's any function Rn to R will have just one output node. Okay, there is one output node by definition because we are computing one value. So, and we're starting with a partial derivative of E with respect to E. Oh, this doesn't make any sense. What is this? Okay, so the partial derivative of E with respect to E is 1. So you take it as this is like a starting point. I mean, you can, if you look into the partial derivatives, you know why exactly, but this is like the starting point. You know, we don't go into the details why this is exactly so, but we can later on if you want. So we started, this is I call it like global output. So the global output is going to be E with respect to the node output. And in this case, the node output is E as well. And this partial derivative will be 1 because it's basically constant. And that's why it's 1. No, it's wrong. No, it's 1 for a reason. Anyway, this is our first step. And then I'm going to look into the next what I'm going to compute now. I'm going to compute the partial derivatives of this node with respect to the children. And I call it local partial derivatives, but it's just a name made up. There is no such a term, but I call this global output. So E with respect to the input, and then E with respect to the parent. So I'm going to compute two derivatives here because this node has two children. One is R and one is S. So I'm going to compute partial derivative of E with respect to R and partial derivative of E with respect to S. Okay. So, and R and S will be some concrete real numbers, and therefore these partial derivatives will also be some concrete real numbers too. So what is going to be, let me just, okay, let me see, what is the partial derivative of E with respect to S? What is the function for computing that? How would we compute partial derivative of E with respect to S? We have this function all defined here. So what is the partial derivative of E with respect to S? So we have this function, or this function. What is the partial derivative of E with respect to S? Yes, it's R. Why is it R? Exactly. So exactly, because we're taking so S will be a constant, and R is what we have. There's the variable for derivating. So something times constant, and derivation of that is the constant. Like we had this C times X, and the derivative of that was just X. Sorry. Oh, no, C. So this is same here. So this is something times constant, and the derivative of that will be the constant. Okay, so this will be S, right? So what is the partial derivative of E with respect to S now? R, yes. Yeah, that's easy, right? I mean, we know that. This is a very easy function, and we know what the derivatives are. We can really compute them. So this is R and S. Okay, cool. We're done. So we know how to compute local derivatives. So we know how these local partial derivatives are. So let's move on. Okay. Well, okay. The answer was here. So I don't know if you look. I hope you didn't look at the answer, but I put it here. I have noticed. So this is easy. We know how to compute it. Now we proceed to the next child, R, and again compute the global derivative, so partial derivative of the output with respect to this input. Okay. So we use the chain rule. What is the derivative? What is this? So chain rule, E to should be R, sorry. R is the chain rule, which is partial derivative of E with respect to E times, well, we can just leave it alone, partial derivative of E with respect to partial derivative of R. Yeah, this is kind of unwieldy, but we have this already computed. So this is 1, and we're multiplied by this, which we already have as well. Okay, cool. I'm just writing what's here. Okay, anyway. So now we know how to compute the partial derivative of the output with respect to this node output. This is cool. So this is just a chain rule. Okay, makes sense. This is what we know. Nice. Which means then we can, for any input, we can compute a partial derivative of this output. So then what are we gonna do next? We move to the next child here to the S. So we were here. We took a first child of E and look here, and now we're gonna take a next child of E and look here. So we're iterating over the childs of the node, like a breadth search sort of from the top. Okay, so now we're interested in the, again, partial derivative of E with respect to S, which is again the chain rule. So the parent's partial derivative and times the child's partial derivative. So we end up with this formula. Okay. Does it make sense? Good. So what's the next step? Where are we gonna go now? What could be the next steps? Next step. What's still missing? What are we going to compute now? Any idea? I mean, you see the pattern already. We started at the top and just iterated through the children. So any idea where to go next? Yes? Yes. So which one, for instance? Okay. So what we gonna impute? What do we want to compute now? Yes. Yes, we want to compute the partial derivative of R with respect to A. Well, what we actually want is the partial derivative of E with respect to A, but we'll use this in the computation. So we start with the first local partial derivatives with respect to the arguments. So this function has two arguments, A and B, and we choose A first. So we want to compute partial derivative of FR with respect to A, and then the next child will be B. So we want to compute partial derivative of B with respect to, partial derivative of R with respect to B. So how do we do that? Okay, so what is the partial derivative of R with respect to A? What is this? And don't look up. Okay, don't look up. There's the answer already. So what is that? So R is A plus B. So what is the derivative of this function with respect to A? Yeah, it's 1, exactly. It's in the title, but if you haven't seen that, then so this is going to be 1. And again, the partial derivative of R with respect to B is going to be 1 again. Okay, this is nice. This is a nice function. Yeah. So that's what we have here upstairs. Okay, so we have the local derivative, and now we need to compute what? Having these local derivatives, we're also interested in the global output derivative. Exactly. We're now interested in partial derivative of E with respect to A and partial derivative of E with respect to B. Okay, so we have, you see the pattern. So all the time we have two sort of derivatives. One is the intermediate derivative of this function with respect to its arguments, and then the derivative of the function with respect to the global output. Sorry, the derivative of the global output with respect to the local kind of node. Okay. And we're using these local derivatives for the chain rule, basically, because the chain rule is sticking together these local derivatives on the path and multiplying them to get there. So, okay, now, but the goal was partial derivative of E with respect to A. Okay, how is that going to be? So partial derivative of E with respect to A is the parent global derivative. Okay, that's what we know already, times the local derivative. Ah, that's easy. We don't have to compute partial derivative of E with respect to R again because we computed it in the parent node already. Ah, that's cool. So we don't have to compute the full chain. We just take the parent because we computed things already for the parent. Ah, that's clever. So we have this. Now, if you look at B, okay, we can't do that for B because B is still missing what? B is missing here the local derivative, right? We haven't been here. We haven't computed we still need S with respect to B, right? This is what we need here because this hadn't been covered. Okay, so let's have a look. So what is the derivative? Don't look up. What is the derivative of? It's like, how is it like? You don't think about white polar bears, and you start thinking about white polar bears. I think it's sort of a joke or something, like a cognitive biases. So don't look up the result for the partial derivative of S with respect to B, which is going to be, well, it's easy. So here's the function, and what's the partial derivative of this function with respect to B? It's going to be 1. Okay, yes, that's easy. So this is 1. This is the local partial derivative of this function with respect to all its arguments. So we have just one argument B. Okay, so now we have all the paths coming to B as well because we have that and we have that. And now we want to compute again the global with respect to B. So here, for this path, we had just one path, basically one path coming in here. So we use the chain rule. Here we have two paths coming into B. So one is through the R node and one is through the S node. Now we're coming to the theory, which should make it clear a little bit why we are talking about this multivariate. I'm looking at you like in the second row. Why we end up here is the multivariate chain rule, because now we're taking, in order to compute this, we need to take all paths coming from all the parents and sum them up. So it's going to be, oh, I'm sorry about this. Yeah, well, what is here? It's partial with respect to B. Okay. So here we take all parents. So R is one parent, and take the global multiplied by the local. Okay, multiplication. So these are these two. And then we take another parent, which is S in this case, and take its global derivative times the local derivative. Multiply and sum them up. So this is the chain rule of multivariable things that we saw a couple of slides before, and you were asking, yeah, I hate this theory. So this is why it works. If I didn't show you that there's a rule for doing this, you would be asking like, why is the plus here? Why does it make sense? So that's why. There's multiple paths, and I'm just summing them together because of this theorem. So okay, so we computed partial derivative of E with respect to B. Okay, what we just did? Some sort of local computations and global computations, and it looks like, oh, that's a mess. But wait. Now we have what we wanted. We have the partial derivative of E with respect to A, and we have the partial derivative of E with respect to B, which is what we are aiming for. We need the gradient. We want to know how the function changes with respect to, you know, the global gradient, so to say, which we called, with respect to the variables. This is what we want. We want the gradient of the function to be able to compute at any point. Does it make sense? And you might be asking, why the heck are we doing this sort of, you know, complicated functions? Yeah, this graph could be super huge. There could be super many functions in there. And all you need for each of this function to make it work is to know what's the parent's gradient with respect to the output, and what's the local derivatives with respect to the arguments. Once you can compute this, you can do arbitrarily crazy with the function. You can compute any function you want, expressed as a computational graph, and have a tool which just goes through the nodes of the graph in some topological manner or whatever you want to do, some search or something. Just go through the children and compute the gradients. And then you end up with the gradient. The thing is, let me see. Okay. So if we are interested in computing, okay, this is interesting. So if we are interested in computing a value, so A equals 0.5 and B equals to 0.7, maybe. These are concrete numbers. So can I now compute the gradient of this function, like the actual value? How can I do that? Yeah, I can do it easily. So what I first need is to compute the output of the function. So what is E? What is the value of E for these numbers? How can I do that? Well, I'm going to ask the output function, what is your value? And it's saying, well, I need to compute R times S. Okay, what is R? I don't know. So let's ask the R function. Hey, R function, what is your output for A and B? And the R function says, oh, I can compute that it's A plus B. Okay, cool. I'm coming back. So I know what R is. Cool. Like actual numbers. So it will be 1.2 is R. Okay, what is S? Well, I don't know. Let's ask the children function. Hey, S, what is your output? And S says, yeah, for B, it's actually just a B. So I know what it is. It's B plus 1, sorry. It's B plus 1, so it's going to be 1.7. Okay, so I know it's 1.7 plus 1 and 1.2, and this function F1 is just multiplication, so I multiply these two together, and it will be some number. 1.2 times 1.7 is 1 point something. I have no idea. So whatever. So I have the output. Okay, cool. And then I'm gonna ask, okay, what is the derivative? What is the gradient with respect to these inputs? So if I'm at point 0.5, 0.7, what is my values for the gradient? Okay, so I'm gonna start here. I'm gonna start, the global derivative will be always 1. This is good. And I'm gonna say, okay, what is my partial derivative of E with respect to R? Yeah, that's what we already computed before. It was, what was that? S. Ah, but wait, I know what S is already because I computed it already. Because I know it. It's gonna be 1.7 or something. Okay, well, I computed it already, so I know the gradient. That's cool. What's gonna be the gradient of partial derivative of E with respect to S? It's the value of R, and I computed R already because I did this forward pass computation. I started here. I know the value, so I know this value already, and I know this value already. Cool. Move on, and so on. So you continue. Basically, you're reusing the computation which you did before for computing the gradient, so you end up with concrete numbers for the gradient very effectively. It's called also like dynamic programming, where you store intermediate outputs and just reuse them later, right? So we're storing all these intermediate output values because we need them for the computation of the gradient. If you think about it, it's basically the chain, the rule chain implemented in a sort of like graphical manner. You would do the same thing with the rule chain. If you do it on paper, there was this example, we had just one variable, the chain rule, and there was this function which was repeated 3 times or 2 times. So we would use the computations, we don't have to repeat the computations again, we just cache it, so to say. And that's the same thing. Okay, maybe it looks slightly ugly here. Maybe if you see it for the first time, I would suggest you just work through this example again and try the computations again for some particular numbers that you really understand what is it doing. So it's really my suggestion. Like you have to actively engage with these computations to understand it. Once you understand, you will see it's fairly easy, so to say, because it's just you compute partial derivatives, which you can do for any function, and then you just multiply them together, or the algorithm will do for you. So any node in this computational graph is a function, right? So we had it before, and it has arguments, so many inputs, and it could go to many outputs as well, right? Many nodes. And we just need, so we can compute, so computing the so-called like a global gradient with respect to this function, to this node, is just summing up this global gradient of, partial of E with respect to H1 and partial derivative of E with respect to H2 and so on, and sum them together. So plus. So this is the multivariate chain rule. So this is how we get here. This is a general formula. Why? An example will be here the node. So I'm in this. It's a constant function. Basically, it's a node, but I'm taking the parents, their partial derivatives, and multiply by this local derivative and sum them up together, right? So times h and to this f, so partial derivative of h1 with respect to partial derivative of f times and so on. Okay, so this is the sum. Okay, and then for each node we need this so-called local derivative, which is again the partial derivative with respect to each input. So partial derivative of f with respect to a1 and a2 and so on. So we compute this for each node and proceed to the children. Once you do it, you end up with what you want with the gradient. Okay, does that make sense? Any questions? So I have a question. So, well, I don't have a question. I mean, I have the answer already. So I would ask you, like, what do you need to implement for each node? If you need to implement a node in this computational graph, well, you need 2 things. Again, you need to know how to compute the output of this node, right? For instance, you need to know that this node is a plus b. So you need to you know how to compute a plus b, right? It's a plus b in Python, basically. So you know how to compute that. And you need to know how to compute partial derivatives with respect to parameters. Yeah, well, we had it as well. So if we had this function r, a plus b, so the partial derivative of r with respect to a is 1, and with respect to b is 1 as well. And in this example, it was partial derivative was here of A with respect to R was S, and partial derivative of E, and so on. So you know how to compute it as well. That's all you need to implement. So any node has to be differentiable. So this is what we, right? Any node is differentiable because it needs to compute partial derivatives with respect to parameters, and that's all you need to implement for this thing to work. Any questions? So let me see how many slides we still. Okay, we're done almost. Okay. And the thing we just learned, it's called backpropagation. It's the backbone of training deep neural networks for last 40 years. That's what you use when you want to train neural networks. You train neural networks by minimizing some function, which we started with. And how you minimize a function is to use the multivariable like gradient descent, basically. So you look into the steepest descent and go there and go there and go there, end up with the minimum. That's how you train it. And how you effectively compute this gradient for these very nasty functions is to use this computational graph and a thing called backpropagation. Why is it backpropagation? Because we have sort of two passes. So we talked about it already. Forward computation, we just compute the outputs of all nodes, right? We start, that's what we did here. We say like, yeah, give me the output. Well, I don't know. I'm asking the parents, the children, I'm asking the children, and you output basically recursively the output for each of the node. Cool, yeah? This is the forward pass. So you end up, you know what the error is at the output, like the value. And then compute the overall functions or the global overall functions partial derivative or the global derivative with respect to each node. Yeah, we did that already. We started at the top and just asked, what's the derivation, and use a chain rule, basically multiplying and summing up together. And how to, sorry, why is that so? Anyway, it's at Rome and Mac. How do you order the computations? Well, it depends. You have some topology. You start with the children first, something like that. But eventually, you need to end up with all the nodes. So it's up to you to design that. And that's it. That's backpropagation. You just learn backpropagation. If you watch on YouTube backpropagation, there's like thousands of tutorials, and they give you, each of them will give different angles. So you might watch them as well. I use the path of just, we actually haven't talked about. Yeah, okay. So just recap, and I'll go to the point. We can express any arbitrarily complicated function as a combination graph, right? You can try yourself. Take any function, you will be able to do this as a simple composition of any functions you want. That's gonna work. And for computing the gradient at a concrete point, so at some point of the function, we just run the forward pass and the backpropagation. So we compute all the outputs and just then compute the gradients by looking at the parents and multiplying and chain rule and stuff like that. And the caching is avoiding repeating the computations, right? So if you cache the intermediate results, you get an efficient algorithm, the dynamic programming. So the takeaways today, now you should be able really to implement it with some effort. You can find a minimum of any differentiable nested multivariable function. It's an achievement. Congratulations, you are able now to understand how to compute a minimum of any multivariate functions, like a Rosenbrock function. You can do that with backpropagation. It will work. Or any other function, which is like thousands of variables, you will find a minimum. And you will find it efficiently when you implement backpropagation. You will find how to compute derivatives efficiently. You don't have to do anything by hand. You don't have to write partial derivative of this bloody thing per hand. You just let it express as a computational graph. And for each of the nodes, you only need to, the nodes are just simple functions like plus, minus, whatever, sinus, exponentiation. And you know the derivatives already. So this is easy to express. You can program it easily. And that's all you need to know. So you can compute the gradients efficiently. The point is, we haven't talked about neural networks at all today, at all. We know how to train neural networks, but we didn't talk about neural networks. It's not a bug, it's a feature. Because this is independent of any neural network. And neural networks, as we will see, are just functions, right? But now we know how to minimize any function efficiently with gradient descent and backpropagation, we can do anything we want, including neural networks. So this is like the backbone of training of GPT, for instance. Yeah, GPT has been trained using stochastic gradient descent, the implementation of a computational graph, and this sort of things we learn today. So you should be able to train GPT as well. Why did we talk about neural networks today in this training of stochastic gradient descent? Because, well, these are two different things, and each of them have their own complexities, but we don't have to go into neural networks in order to understand minimizing functions, right? This is like independent of anything. Okay, so this is good. But so next time when you see like any tutorial on backpropagation, you will see neural networks and the layers, and it's like, yeah, you don't need this actually to understand minimization with backpropagation. You just need a computational graph. Fair enough. Whatever the graph is, that's fine. All right, I think we made it. Any questions? Cool, thanks a lot. So I would appreciate if you put something like we should do on the next exercise. You don't have to, but if you have any idea what you want to go into, yeah, put it in Discord latest like Tuesday, so I have some time on Wednesday to prepare it. Okay, that would be really cool. So thanks a lot and have a great weekend.